Can you see my screen?
Yes, but not the presentation mode.
Yeah. Okay. Thank you so much for organizing this and this opportunity to share our work. I really appreciate the effort you have taken. So the work I'm presenting today is on magnetic skyrmions and multilayer thin films and their electrical signatures, especially the topological Hall effect. The work is done with Professor Christos Panagopoulos group in NTU Singapore. As I said, right now I'm out of that group. So there are significant contributions from my colleagues within the group and also collaborators across. So we had low temperature MFM collaboration with Professor Ophir at Technion Israel, and then theoretical insights into this effect, both from Russian group, Dr. Igor Rojansky and his team, and Professor Ingrid Mertig and her team in Germany. To start with, these magnetic skyrmions are non-collinear spin textures. They're stable, topologically protected, and they are small in size, up to a few nanometers in size, and can be manipulated by electrical currents or magnetic field or thermal gradients. They're attractive, especially when they are seen at room temperature, when they can be controlled in their properties such as size or density, simply by changing our material choice. So here you see a range of material combinations which came up in last 4 or 5 years and really took off the interest at room temperature magnetic skyrmions. So to think of the formation of these spin textures in terms of magnetic interactions, they are a result of competing magnetic interactions of aligning forces and twisting forces, for example. So in this case, an exchange interaction versus Zylowczynski-Moria interaction. Exchange interaction would try to align them parallel to each other, the spin moments, while Zylowczynski-Moria interaction introduces a twist between that alignment. So to think of their formation in terms of domain wall energy, for example, as you can see here, as you can see here, immediately the moment we introduce DM interaction, the formation energy of this kind of tiny spin textures lowers significantly. And there's a critical DMI above which these textures can be seen as stable configurations. So this thermodynamic stability parameter called kappa is a ratio of DMI strength to the critical value of DMI crossing the domain wall energy across this neutral point. So to think of the electrical signatures of these tiny domains, what we see here is any spin polarized current interacting with this kind of spin textures, assuming a strong coupling between the spin alignment of the charge carriers and the local magnetization of the skyrmion itself, the spin moment of the charge carriers is continuously adjusting to the background direction of the spin moments of skyrmion spin texture. What that produces, such coupling between charge carriers and spin textures, produces a measurable Hall effect, which we call as topological Hall effect, which is unique to the skyrmion twisting. So this behaves as though skyrmion itself is producing a magnetic field as compared to the external magnetic field one would apply in a normal Hall effect. So to extract the component corresponding to the magnetic field coming from the skyrmion itself, one can experimentally just measure the total Hall resistivity and understand the total Hall resistivity in terms of different contributions. For example, there are 3 contributions in a ferromagnet that can produce skyrmion spin textures. There's an ordinary Hall effect, which is typical for metals or semiconductors, which responds to the external magnetic field. And then there's anomalous Hall component, which is coming from the magnetic behavior of the system. And then there's additional component, which is unique to the skyrmion spin textures. So experimentally, it's possible if one to measure total Hall resistivity and also estimate the ordinary and anomalous Hall components. The difference of those would be accounted for contribution from the Skyrmion spin textures, which we call as topological Hall effect. The magnitude of such effect can be understood in terms of spin polarization of the charge carriers and the density of the charge carriers and the density of Skyrmion spin textures they're interacting with. Very interesting thing here is that one can purely understand the electrical magnitude of this effect simply by following this formula and estimate the density of our population of Skyrmions contributing to such magnitude. On the other hand, if we were to look at them in real space imaging, we can also estimate the density of such Skyrmion spin textures. So one can approach the configuration or density of these spin textures from two different experimental tools. That combination really gives a powerful tool for understanding the phenomenon in this kind of systems. So when we combine such real space imaging and transport, for example, for B20 Skyrmion crystals, the density estimated or reflected in the transport experiments, which I call NSK-THG, is almost or approximately matches the density estimated from imaging experiments. Here match is roughly up to 80 to 90%, which is already good. But the problem arises when someone tries to study electrical signatures of these Skyrmion textures in interfacial systems. The problem is that the topological Hall magnitude or Skyrmion density reflected in the electrical signatures is way higher than the density of these features reflected in the imaging experiments. And the discrepancy can be like few orders of magnitude, which is very different from what is seen in the B20 Skyrmion crystals. One need to notice that this range of materials reporting or studying this kind of effect in interfacial systems are looking really at different Skyrmion configurations in terms of temperature, field, and their magnetic interaction strengths. So what is going on? What is contributing to this huge discrepancy is the problem, or at least there were controversial reports and discussions. So to solve or to understand what is going on, the first thing we did was to establish a material platform where we can controllably tune these configurations in terms of temperature, field, and kappa, the thermodynamic stability, which accounts for a combination of magnetic interactions. And experimentally, the quantity of interest would be simply track the ratio of density of Skyrmions reflected in the transport versus density of Skyrmions reflected in the imaging experiment. A typical example of control on Skyrmion configuration in our material system can be seen here, simply by changing relative thickness of iron to cobalt layers in this kind of multi-layer stack. One can change Skyrmion configuration over a wide range of size and density. Once we stick to a particular composition, then further can be, these textures can be controlled by changing temperature and magnetic field. So when we, this is an example of how controlling these spin textures simply by sweeping the field along x-axis and looking at the topological Hall magnitude they produce. Immediately we see here a very counterintuitive observation. A dense arrangement of Skyrmions which appear around 1000 Orsted in this case seem to produce a magnitude which is smaller than the magnitude of isolated Skyrmion phase. So when we sweep the field and control Skyrmion configuration, moving from dense arrangement to an isolated phase, we see a two-peak structure emerging in the topological Hall profile. And counterintuitive point is that though small in number, the isolated Skyrmion seems to be producing larger magnitude compared to the large dense arrangement of Skyrmions. So to start with, this is what we wanted to investigate. So we produce a range of films which show only isolated Skyrmion phase as a function of field, and a range of films which show a dense arrangement transforming into isolated phase as a function of field. So consistently, what we see is that whenever there's an isolated skyrmion phase, either as a function of material or as a function of field, it always produces large magnitude compared to dense arrangement of skyrmions. And when we compute the quantity of interest, which is ratio of skyrmion density reflected in the transport versus imaging, we see a systematic drop in this ratio approaching towards 1 as we increase the skyrmion density. This is a significant observation in terms of what is going on with respect to the skyrmion configurations. The point here is that if we are able to pack as many skyrmions as possible, the skyrmion, the topological Hall effect in the interfacial system does approach B20 skyrmion crystals, which was not the which was the debated point in interfacial systems. I point out that all the observations in the recent times on the interfacial systems are focused on isolated skyrmion phases, not the dense arrangements. So our material, in a way, offers control on this kind of configurations to understand what is going on in this system. So what happens as we go from isolated to dense arrangement? A quick analysis in terms of the lattice configuration or the configuration of skyrmion texture points out that as we increase the density of disordered hexagon lattice phase emerges with as a function of skyrmion density. As you increase the skyrmion density, for example, the nearest neighbor coordination number approaches 6, and their angular orientation increasingly focuses around 60 degrees, which is the characteristic of hexagon lattice phase. Indeed, this kind of transition is expected or called a second order phase transition of nucleation type. What this does is a skyrmion lattice, as it dissolves and becomes a trivial ferromagnetic phase, it goes through a phase of isolated skyrmion configuration. So this is in fact understood in terms of second order phase transition, but no one has seen how this affects the topological Hall effect. So how does this affect the topological Hall effect in this kind of systems? To answer that question, first we establish the boundary between this transition between isolated and lattice phase over a wide range of temperature and magnetic interaction strengths. So if we do some laborious imaging experiments, it's possible to track this boundary as a function of temperature as well as magnetic interaction strengths. So what we did is then to track the magnitude of the topological Hall effect across this phase diagram as we go from isolated phase to lattice phase. What we see here, either you move along the temperature. Strictly in this case, we are not fixing the kappa vertical line, but largely if you change the temperature, which is also changing kappa in this case, we see a local maximum emerging in the topological Hall magnitude whenever we are around that transition region. And that is also true if we fix the temperature and sweep the...
You have less than a minute, so if you would like to... You're 30 minutes.
I'm almost done. So this local maxima which emerges within the transition region is the source of the large discrepancy people have been saying. So what is the underlying mechanism that works around this transition region? As we already pointed out, it's as a second order phase transition. So one needs to understand what is happening at the transition in terms of critical behavior and critical fluctuations. In this case, the temperature and magnetic interaction strength gives that the control over critical behavior. So in our case, if we cannot tune these two parameters independently, but if we combine their effect by taking an effective temperature as temperature and kappa as a product, one can simply produce a critical behavior phenomena across this transition. So when we combine such temperature and kappa as a function of along the x-axis, a nice power law behavior emerges in the topological Hall phenomenon that we see. So this is at the core of what people have been saying, but they did not realize what is contributing to this large discrepancy between transport and imaging experiments. Most of the experiments are focused very close to the transition, but no one was able to push it into the very ordered and lattice phase, which we are able to do. To summarize, we are able to control the phase transition between these two configurations and understand that in the imaging experiments, and also understand that in terms of critical behavior where the emergence of power law behavior comes up. And that can also be seen purely in the electrical measurements if you track the magnitude of the topological Hall. So these three different approaches conclude that there's a significant improvement in the topological Hall magnitude by accounting for chiral spin fluctuations of second order phase transition, which is what we have found in this system. And this also offers a kind of tunability in this effect. Thank you. And if you are interested to read more on what kind of this critical behavior this transition belongs to, you can look at our paper and see critical behavior or power law scalings in this kind of system. Thank you very much.
That was a great talk. Thanks a lot. Very interesting results, but unfortunately, we do not have time to take questions.
Yeah, I think
sorry for that. You kind of exceeded the whole time in Q&A, yeah, people, if anyone wants to ask questions, you can move to GatherTown, and yes, they can email you. Your email is in the abstract booklet, so you can set up a meeting and have any sorts of interaction you would like. Now we have to move on to Esteban IROULART. Thank you for your talk. So Esteban is from the National University of La Plata from Argentina.
Hello, hello. I'm going to share my screen now.
That's great.
Are you watching it right now?
Yes.
Okay. And if you see some trouble, please let me know, but I start, okay?
Definitely, go on.
Okay, thank you very much, Cristina, and thank you all the organizers for letting me present this talk. I'm Esteban IROULART, and I recently graduated for my physics degree at the National University of La Plata in Buenos Aires, Argentina, and just started as a PhD student, all with the advising of Dr. Diego Rosales. This talk is for my final work for the degree. This is a summary of what's going to be my talk. I shall begin with the introduction and talk about skyrmions. You might already know what magnetic skyrmions are. They are spin textures with some interesting properties, such as a high topological stability and emission electrodynamics. Here on the right, I show a ferromagnetic skyrmion. That's the most common type. The skyrmions have some potential applications that are very interesting, like skyrmion racetrack memories, where the skyrmions can be created and manipulated by spin current and then read. And their main advantage is that they can use much lower current densities than the racetrack memories based on magnetic domains. And this kind of devices motivates our study of interaction between skyrmions mediated by the dynamic of traveling electrons. Another type of skyrmions are the antiferromagnetic ones that can be understood as a superposition of two ferromagnetic skyrmion lattices with opposite spins. Here on the right, I show a picture from the work of Gao, my advisor Diego Rosales, Flavia Albarracin, and collaborators from Nature in the year 2020, where they studied this material and were able to stabilize antiferromagnetic skyrmions in this material through anisotropic couplings. I'm going also to mention the ferrimagnetic skyrmions that are similar to the antiferromagnetic, but the two sublattices of skyrmions have different magnitude, so it leads to a non-compensated magnetization. Here I show a picture from the work of Gu and collaborators, where they studied the skyrmion Hall effect in ferrimagnetic skyrmions in films of gadolinium iron cobalt. I'm going to talk about our work now. We studied a Hamiltonian that's a sum of two Hamiltonians, one related to the electrons and one related to the magnetic degrees of freedom that contains the hopping term, the Hans coupling, the exchange interaction, and the Helsinki-Morija interaction terms. Here we're going to assume that the magnetic relaxation times are much greater than for the electrons, so we can use a Born-Oppenheimer type approximation and study only the Hamiltonian of the electrons, remaining the degrees of freedom of the magnetic lattice frozen. For that, we used a series of numerical ansatz for the spin vector in spherical coordinates, as shown here, where the angles theta and phi have this behavior with the distance. We used a discrete lattice of 200 times 16 sites, where we put the skyrmions and separate them at a distance delta, and used this variable to characterize the energy, and that means it could be an important parameter here. Here are the configurations we obtained. We compare the results we had for skyrmions with ferromagnetic domains inspired by the potential application of skyrmions in Racetrack memory devices, as I mentioned before. We calculated the electronic ground state energy by a diagonalization of our Hamiltonian through an unitary transformation. And since the electronic ground state can be written as a product of individual electronic states, we should simply take the expectation value of the Hamiltonian in this state and have a sum of electronic energies from 1 up to n, when n is the electronic filling that's determined by the Fermi energy of the problem. So we end up characterizing the electronic ground state energy as a function of both the electronic filling n and the distance between skyrmions and delta. In order to comprehend the effect of Hans coupling, we suppressed the energy without any type of coupling, I mean with J equal to 0, that can be calculated exactly. And then we also calculate an effective force as a derivative of this electronic energy with respect to the variable delta. I'm going to present our results now. Here on the left, I show a plot of the electronic ground state energy, and on the right, the effective force as a function of the distance delta in the
Yeah, I think we cannot hear Esteban. Is that right?
Yeah, we might have lost him.
Yeah. Maybe I can try to text him.
Oh, Esteban, you back? We'll have to mute him first.
Okay, can you listen me now?
Yeah, we got you now.
Okay, I don't know where I lost you in the previous slide here.
You have to share your screen again.
Oh, okay. Of course. Right? Are you watching my screen, right?
Yep.
Exactly. You were in this slide, I think.
Okay. Sorry about that. I don't know what happened. I was telling that we show here the results of the electronic ground state energy and the effective force as a function of the distance delta for different fillings. We note here that there is a minimum in delta equals 0. That means that when there is one electron coupled, the skyrmions tend to be one next to each other. But if we increase the filling, we see that there are local minimums in the energy that can mean if we could create the skyrmions and separate them at a distance delta like this, we could have a stable configuration, and by that I mean a local minimization of the energy configuration, and that will be very useful for the potential application in an electronic device, for example. With increasing filling, we see this oscillatory behavior with the distance for the energy, But if you go to higher fillings, we see that the behavior, the oscillatory behavior is lost, and there is a different pattern here. For the case of antiferromagnetic skyrmions, the results are quite similar to the ferromagnetic, but for the first fillings, but we see the oscillations in the curve of the force and in the energy proper of the antiferromagnetic nature of the lattice. If we increase the filling, we note again the oscillations in the energy, but the difference here is we note this pattern of local minimums and maximums at higher fillings, in contrast to the ferromagnetic ones. For the strong coupling limit, here we compare the two types of skyrmions, were quite similar. The results were quite similar, but we see the difference here was that the antiferromagnetic skyrmions have energy with greater amplitude of oscillations, and we could say that they are much more stable than the ferromagnetic ones. The most remarkable result, perhaps, of our work was the one we obtained in the higher filling region for the strong coupling limit in antiferromagnetic skyrmions. We see this interesting pattern of well-defined local maximums and minimums that again could be very useful if we could create the skyrmions, the antiferromagnetic skyrmions, and separate them at this many distance delta for example, the application in an electronic device, as I mentioned before. All that I just told can be compressed in these phase diagrams that are density plots of the energy as a function of both the electronic filling in the y-axis and the distance delta in the x-axis. We see here that even though the behavior is quite the same for the first fillings, if we increase the filling and go up in the y-axis, the pattern is quite different in the three kinds of textures, and the most interesting one is the pattern observed in antiferromagnetic skyrmions. Moreover, in the strong coupling limit, where we see these stripes on the filling axis, remarking again the stability of this kind of skyrmions. Lastly, we calculated the electronic density by taking this expectation value in each site and doing a method similar to the one we use in the calculation of the electronic ground state energy, and we plot the results. Here I show a magnetic configuration of two ferromagnetic skyrmions at a fixed distance delta, and below we show the plot of the electronic density in the lattice. Here purple represents the lowest value of the density and red the highest. We see here that the electronic density remains null in the region where the skyrmions are, and there are electronic modes in the region between the skyrmions that will act like a potential barrier for the electrons. If we go to higher fillings, we see even more electronic modes, but we notice that the skyrmion structure is beginning to lose and ends up losing for example, 100 electrons, where we see that the electronic density is almost a continuous one. And that's okay, because we know that the ferromagnetic skyrmion configuration is a smooth one. So the results were in agreement with that. For antiferromagnetic skyrmions, we see the same results for the first fillings. And if we increase the filling, we notice that the antiferromagnetic skyrmions act like a hard core for electrons, remaining this structure stable as we increase the filling, and the antiferromagnetic skyrmion remains in a hard core state for the electrons. So again, we could conclude that the antiferromagnetic skyrmions is a much more stable kind of texture. And finally, we compare with ferromagnetic domains. The behavior is the same for the first fillings, and then it started to look much more like the antiferromagnetic skyrmion. But if we increase even more the filling, we see the presence of these electronic modes that are spherically symmetrical in the region inside the domains, in contrast with the obtained for the skyrmions. So I'm going to the conclusions now. We study the behavior of the electronic ground state energy and as a function of both the electronic feeding and the distance delta. We saw the oscillations in the energy for the three kinds of sectors we studied, but we saw the pattern of the antiferromagnetic skyrmions was the most interesting, as we see in these stripes in the feeding axis for the phase diagram, in contrast to the pattern observed for the other kinds of textures. Then we calculated the electronic density in each site, and we saw this hardcore state that antiferromagnetic skyrmions form. And again, we can highlight the antiferromagnetic skyrmions as promising candidates for electronic devices when we will be able to apply in a possible electronic device. We also like to propose for future study the study of the effect of the skyrmion, and then study skyrmion and anti-skyrmion pairs or pairs with different topological charge, and the study of the whole conductivity. And that will be all. Thank you very much.
Thank you. That was a great talk. So we give you 1 more minute extra for the technical problem. And we are ready to take questions. Please raise your hands. So in your work, do you take boundary conditions into consideration? Because I always see that you show results on a stripe. So I was wondering.
Yes, yes. As we see here, for example, here we see that okay, and the boundary conditions here are periodic because there were a third skyrmion here, and we see here that the electronic density is have an electronic mode here as a maximum. We also applied open boundary conditions, and the results were quite the same, but we used mostly the periodic boundary conditions.
I see, thank you. This is the result of micromagnetics, right?
Sorry?
What is the computational technique? Is it micromagnetics, or how do you calculate the interaction potential?
We used these numerical ansatz here. Let me go to back. You mean this part for creating the skyrmions?
Sure, okay, I understand. Yeah, thank you. Jason, you want to introduce the next speaker?
Yes.
Thank you very much, Cristina.
Thank you, Esteban.
Thank you.
We have our next speaker, Golam, from the University of Virginia. Let me put him in the spotlight.
Hello, can you hear me?
Yes.
Okay, so I was having trouble while unmuting myself. Yeah. Thank you, Jason, for the introduction, and good evening, everybody from my side. And I would like to thank all the organizers for giving me this opportunity to talk at this platform. My name is Golam MORSHED. I'm a PhD student at the University of Virginia. The title of my today's talk is Positional Stability of Skyrmions in a Racetrack for Memory Application. Although the previous two speakers have already talked about Skyrmion a bit, but for the sake of the completeness of my presentation, I will start with the motivation, like why we are using Skyrmion for this. So as we might all know, like skyrmions are topologically protected spin textures, and they are recently emerged as potential candidate for their attractive features like ultra small size and particle-like nature, and they are like emerging for the memory and logic application. So one of the prototype memory element is the Racetrack based memory, and for a Skyrmion based Racetrack memory, it can be useful for both conventional and unconventional application. So here is an example for the Skyrmion based Racetrack for a conventional application where the Skyrmion can be encoded by bit 1 when Skyrmion is present in the Racetrack, and it can be encoded as a bit 0 when Skyrmion is absent in the Racetrack. So here in our group, we where the incoming wavefront's temporal data is mapped into the position of the skyrmions, and the skyrmion positions can be used for the encoding of the information. So this is basically a prefabricated skyrmion, and we are shuttling the skyrmion through electrical current, and their different positional coordinate is basically storing the timing information of the incoming data, and this could be used for write, read, recovery, and erase operation. So just a small note here, like here, write or erase doesn't refer to the nucleation or destruction of the skyrmions. Rather, it basically refers to the coordinate position. And for reading the skyrmion, we use normal magnetic tunnel junction, and which is basically located at the end of the racetrack. So the read operation would be destructive. That's why recovery racetrack is used to retain the original position of the skyrmions, which can be shown in the top left figure. So also, although skyrmions have attractive features for application, they have their own challenges. Like skyrmions are susceptible to thermal fluctuation, and they exhibit Brownian motion. And skyrmion doesn't stop like immediately when the current removes, so it has an inertia-driven drift velocity as well. And skyrmions annihilates at the edges due to the skyrmion Hall effect. And skyrmion can be pinned at the defect for a non-ideal racetrack. So this brings us to the question, like, can we hold the skyrmion for long enough time while retaining their original position? Because this is important. If skyrmion position changes, so the bit 0 or 1 can be like cannot be read reliably. So here we show like how the skyrmion can be locally stored, and it can be moved without annihilation when needed. So one of the approach to avoid such undesirable motion of skyrmion is to create defect or notch in the racetrack that can hold skyrmion locally. So in this figure, the black semicircular region are basically the defect that may be a difference material parameter than the rest of the track region, or a notch, which is basically a missing material from that particular part of the racetrack. So we show that this notch or defect can give long enough lifetime to hold the skyrmion locally for particular application. So the lifetime of the skyrmion can be calculated through this Arrhenius-like equation, and we can see that energy barrier by energy barrier we can tune the lifetime of the skyrmions. And for the long-term memory application, like around 40 kT energy barrier is needed. Like it gives 10 years of close to 10 years of lifetime. So we do micromagnetic simulations in this type of geometry with defect and notch by employing the minimum energy path calculation. So we basically let the skyrmion pass from one side to the other side of the defect or the notch, and calculate the minimum energy path for the trajectory of the skyrmion, and from there we calculate the energy barrier. So here we show the results for the case of anisotropy defect. That means the anisotropy of the defect region is different than the rest of the track region. And we show the results in the right side for a 800 by 200 by 3 nanometer racetrack with a defect radius of 75 nanometer. And we vary the ratio of the anisotropy and find that when the ratio is around 2, the energy barrier is kind of saturating. So for the rest of the calculation, we use that anisotropy ratio. One small note here, like in the x-axis, we show the image index, which are basically the snapshot of skyrmion path when skyrmion passes from one side to the other side of the defect, and we basically plot the minimum energy corresponding to this particular position of the skyrmions. So here we show the energy barrier for the case of racetrack with 75 nanometer radius of defect, and we vary the material parameter DMI, and we find that the energy barrier is basically increasing when DMI increases, which is kind of expected because as the DMI increases, the skyrmion size basically increases. And when skyrmion size gets bigger, it is difficult for the skyrmion to pass over the space over the defect, and it sees basically higher energy barrier. We also vary the material parameters like the geometry of the materials, like the defect radius, and find that as the radius of the defect increases, it also gives higher energy barrier for the same size of skyrmion. So it is kind of obvious, like when the defect size increases, it left a shrink space over the defect. So basically the space over the defect is decreasing. So it is even harder for the skyrmion to pass through that region. Although this anisotropy defect can give long enough lifetime for the skyrmions, but for practical application, it might be difficult to maintain the ratio of the defect region and the rest of the track region. So we use another type of defect here, which is basically a notch. That means a missing material from the racetrack. For the same dimension of the racetrack, we vary the DMI and also the notch radius, and the results are shown here. Their characteristics is kind of similar as the previous case, but here, like for the notch case, we get a higher energy barrier for the same size of skyrmions. And we find that for this case, like when skyrmion trying to pass over the notch, so the radius of the skyrmion shrinked much higher than the previous case. Like in the figure D, you can see that like when the skyrmion is passing over the notch, its radius basically reducing from the initial position. And this change in radius basically responsible for this energy barrier. And also when we are increasing the notch size, the change in radius is increasing, which is kind of proportional to the energy barrier we are getting. So we vary a series of notch radius for a 3 nanometer thick film here, and shows the range of the energy barrier we get. And we can see that we get like around 40 kT energy barrier, which might give like a year-long lifetime. And this energy barrier can even be increased by changing the thickness of the film, and the relation of the energy barrier to the thickness of the film is linear basically. So as we increase as we use a thicker film, we'll definitely get like higher energy barrier as we need. So comparing all the data we have by varying the DMI and the notch radius, we try to fit an empirical equation of the maximum energy barrier. So we use a power law type fitting and find that our calculated data is basically perfectly matched with this y equal to ax to the power b type of fitted curve. So so we basically fit the energy barrier in terms of DMI. And obviously the constant A and B are related to the notch radius Rn, and they are linearly related. And by combining all these three, we get this fitted equation here, where the prefactor are basically materials dependent. So far, I talked about the energy barrier, but the other important thing is the unpinning current. So we want to optimize the energy barrier in such a way so that we can get long enough lifetime, but at the same time, the skyrmion should be unpinned with a moderate amount of current, because if the unpinning current is very high, then there would be joule heating, and also the high current may nucleate additional skyrmion, which is not expected. So here I show the unpinning current results for both type of defects with a defect radius of 75 nanometer and a 3 nanometer thick film, and we find like the unpinning current is in the range of 10 to the power 10 or close to 10 to the power 11, which is moderate and very encouraging. To show you the unpinning process for this case, like up to 4.5 into 10 to the 10 ampere per meter square, the skyrmion cannot pass through over this notch, but when it just cross that value, it like pass through over the notches without annihilating. And the next thing is basically like when you want to use the skyrmion practical application for multilayer operation, the skyrmion Racetrack should be digitized. So if we want to do a n-bit operation, we need 2 to the power n number of notches, and the skyrmion will be localized within the space between 2 consecutive notches. So here we show a simple case of like 2-bit operation. So we arrange 4 identical notches equally spaced from each other, and we find that they have exactly same behavior. So for a 5 nanometer thick film here, we get like 40 kT energy barrier, which is obviously give a year-long lifetime. And the unpinning current is also in the range of 10 to the power 11, which is less than the current that normally domain wall based circuitry have. So this brings me to the summary for my today's talk. So we basically showed like the skyrmion can be localized through this engineering of the racetrack by defect or notch, and we can get lifetime that can hold the skyrmion for long enough time. And also the unpinning current are moderate for this case. So we believe like our results can be useful to design practical skyrmion based racetrack geometries for spintronic application. So I would like to thank my colleague Hamid Bakili and my professor Ofikosh for mentoring me during this project, and also the funding agency DARPA. And thank you very much for your attention. I hope I mean I finished before the time, maybe.
Not really. I think we should take questions now.
Yeah.
Arindam?
Hi.
Yes.
Hello. Can you hear me?
Yeah.
Yeah, that's very nice presentation. Thank you. Can you go to slide number 6? I mean, actually, not slide 6. I mean, in every slide where you mention the energy, that barrier energy EB, what was the term? I mean, you mentioned that you use mu max. So is it the total energy or anisotropy energy or exchange energy?
So this is basically the total energy, but this is the total energy difference from the initial position of the skyrmion through the other position when it's like move throughout the racetrack.
Okay, I mean that means that let's say at x equals to x1 the energy barrier is E1, and at x equals to x2 energy is E2, then
yeah,
the plot is basically E1 minus E2.
Yes, exactly.
And it's the total energy.
Yeah, the total energy, yes.
Okay, thank you.
Yeah.
Is there another question? I don't see currently any other question, and we're out of time. So thank you, Golam. That was a great talk. It was very interesting.
Yeah, thank you very much for your attention. Yeah.
Whoever's interested in Golam's work, they can reach out to you by email and you can arrange a meeting on the virtual space. So yeah, me and Jason are about to head out, and Purnima Balakrishnan from the National Institute of Standards and Technology, together with Saima Siddiqui from the University of Illinois at Urbana-Champaign, will take over to moderate next questions. So Purnima and Saima, whenever you're ready.
Hi, so.
And thanks, Jason, for the great work. Thank you.
Thank you, Christina.
Thanks, Jason and Christina. So our next speaker is going to be Santiago Osorio from Centro Atómico Bariloche in Argentina. Go ahead and start sharing your slides while I unmute you.
Okay, I will share my screen. Let me, okay, so you can see it?
Yep.
Perfect. So, okay, I am Santiago Osorio. I am a postdoctoral researcher working at the Instituto de Nanociencia y Nanotecnología, Nodo Bariloche in Argentina. I want to thank the organizers for this opportunity to share my work at this conference, in which I will talk mainly about the possibility of obtaining a metastable chiral soliton in a monoaxial helimagnets. So first of all, I want to mention the people I work with. Sebastián Bustingorri and I are here in Bariloche, Argentina, and our collaborators are from Spain, in Zaragoza, are Javier Campo and Victor Laliena. The work I am going to show you is a result of this collaboration. So, in this talk, I am going to consider a monoaxial helimagnets, which, like the compound shown here, with chromium, niobium, and sulfur. The magnetization state is represented by the field N, which is a unimodular field. And the energy contains essentially three terms. The first of them is the exchange energy. The second is the Tsiolkovsky-Morilla term. And the third one is the uniaxial easy plane anisotropy. And we also include the Zeeman term with the magnetic field pointing along the y direction as shown here. The monoaxial character of this helimagnets has to do with a strong anisotropy in the Tsiolkovsky-Morilla term that acts mainly along a specific direction, which defines a chiral axis, which is in this case lays along the z-axis. And for these compounds at low magnetic field, the ground state corresponds to a chiral soliton lattice, which consists of a regular arrangement of chiral solitons. And when the magnetic field is increased, this state survives up to a critical field, which is around 230 millitesla. But it was shown that we can obtain a single chiral soliton as a metastable state, even above that critical field of 230 millitesla. But the limit of metastability is determined by the critical field for the metastability, which is B asterisk, and it is around 1.5 Tesla. So we will focus our interest on the possibility of obtaining this single chiral solitonic state in a monoaxial helimagnets. And we are interested in this object because they could be used for information storage and processing. A key concept or device here is that of racetrack memory, which is essentially a one-dimensional track in which the information is represented by some magnetic state of the racetrack. In fact, nowadays, there are at least two versions of racetrack memories. The first of them is the domain wall racetrack memory, in which the information is represented by domains up or down to represent S0 or 1. The second and more recent, and also we already heard about it in the talk of Golam, and Esteban mentioned something about this also, is the concept of Skyrmion racetrack memory, in which the information is represented through the presence or absence of a skyrmion. Now, a chiral soliton is characterized by a solitonic structure and also topological nature, but they also exhibit a magnetoresistive response. So they could be possible candidates so we can consider these objects as information carriers with applications to racetrack memory. So this raises the question about how to obtain or create an individual chiral soliton. And so we are going to study this possibility. And to attack our problem, we use micromagnetic simulations based on the Landau-Lipschitz-Gilbert equation shown here. Besides the field-like and the damping-like term, we introduce a third term that accounts for the torque due to external current, which is shown here in the third row. J is the current density, and B is a parameter that accounts for the degree of polarization of the current, and beta is the non-adiabaticity constant. To integrate this equation, we are going to use the software MUMAX that provides an efficient framework to do this. So we apply a current which has opposite directions on each half of the system. This setup was used by Comporas and collaborators to study the destruction of chiral soliton in a system with just 2 chiral solitons. But we are going to apply this to a chiral soliton lattice instead, which has many solitons. In this case, we use periodic boundary conditions for our simulations in a system whose size is 500 nanometers. So if we apply a current that grows linearly with time, as shown in figure A, we see that the energy of the system exhibits a series of peaks, as shown in figure B. Each peak is followed by a sudden drop of the energy. And in this case, the magnetic field is 10 millitesla, and the initial state corresponds to a chiral soliton lattice with 13 solitons. So what is happening here is that the current pushes the solitons against each other. At a given time, one chiral soliton is destroyed, which leads to the sequence of peaks and drops in the energy. All this process occurs right in the center of the system. So while the current is applied, the destruction of solitons continues until the system ends up with just one chiral soliton. This can be evidenced by the calculation of the binding number, which we call Q, and counts the number of chiral solitons in the system. Indeed, in figure C, we see that the binding number decreases in steps, showing that the destruction of one soliton occurs at each step. So we start from the chiral soliton lattice with 13 solitons here to end up with just one chiral soliton here. And the corresponding state is represented in this side of the slide, which consists of exactly one chiral soliton located at the center of the system. Now, if we, this is one of our main results, okay? We have shown that we can obtain a state with chiral soliton from the chiral soliton lattice by injecting current, as discussed in the previous slide. Now, if we apply a square pulse instead of the ramp, the number of solitons in the final state is determined by the intensity of the current. So we can obtain a phase diagram that tells us the final number of solitons for a given magnetic field and intensity of the current. Our interest is focused on a state with just one soliton. So in the JB phase diagram on the right, we distinguish 3 regions. The first of them in which Q is equal to zero in blue, which means that we have no soliton there. A second region in red in which we have more than one soliton. And the most interesting region is that in which Q is equal to 1 in white or yellowish, shown here. So it is important to know that this last region is quite extensive. And now this phase diagram is obtained from an initial state that corresponds to the equilibrium or ground state of the system at any value of the magnetic field. So what happens if the initial state is not the equilibrium one, but a metastable state? So to answer this question, we represent the previous, we repeat the previous protocol, but now starting from an initial state that contains a fixed number of chiral solitons. So for example, we show here 4 phase diagrams derived from 4 different initial conditions with 13, 10, 9, and 7 solitons. The hatchet box indicates the field range in which the state with n solitons is stable. So for example, for a state with n solitons, with 9 solitons, sorry, in panel in figure C, this state is stable for the magnetic field within the range 0.13 and 0.18 Tesla, but it is metastable outside this range. And what we see is that the region with Q equal to 1 remains almost unaltered. This is very important because this means that we can obtain a single chiral soliton by applying a current to a chiral soliton lattice, even if the initial state is a metastable one. So our results are quite robust or independent of the initial state, which this drives me directly to the main conclusions. In the first place, we have shown that we can obtain a single chiral soliton from the chiral soliton lattice. So we can also extend our analysis to open systems. In the second place, we have shown that we can obtain a single chiral soliton in a wide region of the JB phase diagram, and this phase diagram is quite robust. And so through the protocol used here, it is possible to obtain a single chiral soliton state in a controlled way, which was the main goal of our work. With that, I end my presentation, and thank you.
Thank you, Santiago, for the nice talk.
Thank you.
Is there any question from the audience? Okay, I have one question. Okay. Have you checked how this annihilation of the soliton with current density depends on the periodicity of the helimagnet?
Yes, sure. Actually, I have some backup slides here. We can extend these systems, this protocol to open systems, but we need to deal with some specific problems that comes from the boundary conditions introduced by the Sierociński-Morilla interaction. And the thing is that if you inject current to an open system, you also inject chiral solitons that enter from the edge of the sample. But you can induce a strong EC axis anisotropy in both edges to prevent this injection of chiral solitons. And the phenomenology then results essentially the same as the one shown for the periodic boundary conditions. So I think this is a more realistic situation, and you can take care about this process of creation of solitons.
I see. Thank you. We have questions from Flavia.
Okay.
Flavia.
Hi, can you hear me?
Yes.
Yes.
Thank you. A short question. Okay. So Santiago, excellent talk. Thank you very much. I would like to ask you about
thank you.
The states where there are many solitons that you said that they were not stable, and are they arranged in a periodical way, or how do they appear? Thank you.
Okay. If you have an n soliton state, they are always arranged in a regular pattern. But this is true if you do not inject the current. When you inject current, what you see, for example, here in this figure 3, you distort the arrangement, and the wavelength changed because of the current. But essentially, if you have n solitons, they will be arranged in a regular pattern. I don't know if that answers the question.
Purnima, did you want to ask a question?
I was just curious if so here you're putting in a current symmetrically from the center, right? can you still create these chiral solitons if the current goes from one end to the other? But
can you repeat the question, please?
So for all of this, you're injecting the current from the center, and it's symmetric, right? Going to each end. Can you still create these chiral solitons if you have, say, the voltage just positive at one end, negative at the other?
I don't know. I think I need to think a little more about that. I don't really know. No, I think okay. So no, I think I need to think more about this.
Oh, that's
sorry.
fine. Thank you very much.
Thank you.
Thank you, Santiago. Yeah.
Thank you.
Okay. Our next speaker is Samuel Liu. He's from the University of Texas at Austin. So Samuel, feel free to start sharing your slide.
My slides?
Yeah.
Okay, great. So, hi, I'm Sam Liu, and today I'll be talking about my work on controllable reset behavior in domain wall magnetic tunnel junction neurons for task-adaptable computation. The work was done at UT Austin in collaboration with UT Dallas and Sandia National Labs, and I'd also like to acknowledge funding from NSF. So first, I'll discuss the motivation and background for the development of neuromorphic artificial neural networks. Then I'll move on to introducing the biologically inspired edgy relaxed behavior that we take advantage of using the domain wall magnetic tunnel junction device. I'll then talk about the methods used for both the micromagnetics as well as the neural network simulations, followed by the results. And I'll finally discuss the figures of merit not limited to the simulations, and I'll wrap it up. So first of all, neural networks are very helpful for data-intensive tasks like image classification, extrapolation, and so on. And traditional von Neumann computing has a lot of overhead in shuttling data in between memory and compute, which is the memory wall problem. So developing neuromorphic hardware systems to alleviate this is important. Neuromorphic systems have the advantage of massively parallel in-memory operations, as well as greatly enhanced efficiency in learning a wide range of tasks. These artificial neural networks are comprised of two components: synapses, which are non-volatile memory elements, and they typically have multiple weights, and neurons, which show integration and fire or leaky integration and fire behavior shown in the figure in the bottom right. As you can see, the neuron state increases where impulses are delivered, that's called integration, until it reaches a threshold, where it then emits a spike, which is called firing. In between input spikes, the neuron state relaxes, which is known as leaking. So we need devices that can emulate these operations. But first, why magnetic materials and devices for neuromorphic edge computing? Well, for a start, for synapses, they can be non-volatile. They have high endurance, they're radiation hard, and they're back end of line compatible. And in particular, magnetic devices also have complex tunable behaviors that can have useful implications for neural network performance, which leads me to the device platform. So the device platform we're considering for these artificial neurons are domain wall magnetic tunnel junction devices. These are 3-terminal devices where the integration state of the neuron and the weight of the synapse are represented by the position of the domain wall. The structure of the device consists of a ferromagnetic track with a domain wall and a sensing MTJ on top. The domain wall is moved by injecting current through the left and right terminals, while the state of the device is read by injecting current through the sensing MTJ. For a neuron, the MTJ is placed at the firing point towards one side of the track, while for a synapse, the sensing MTJ spans a large proportion of the track. The neurons in particular have been demonstrated to implement leaky integration and fire behaviors. And here I'm going to introduce some more advanced biologically inspired functions for inference optimization. So in some biological neurons, like mammalian pyramidal neurons that are related to rhythmic motor functions, there's a period of time after a neuron fires where the firing threshold is lower, shown in the hump in the figure here, called after depolarization, which makes the neuron edgy. So we can use this idea to introduce neuron-based inference optimization for particular data sets. So we can implement this behavior in multiple ways shown in the upper figure. So first, by shaping the device like a trapezoid, so the domain will propagate in the backwards direction. The domain will move towards the thinner direction. By applying a constant external magnetic field out of plane, or by modulating the reset current to not completely reset the device after firing. So in order to show this, we used Mumax3 to simulate the effects of each of these, set up with the parameters shown in the table here. 80 microamp current pulses of 1 nanosecond in duration are applied at varying period lambda to show this. Based on all examples, the higher the frequency of the pulses, the edgier the neuron is, with a marked difference in the firing threshold for the varying frequencies. For example, in figure A in the top left here, in the plot of domain wall position over time, the domain wall position at 40 nanoseconds is closer to the firing point for the higher frequency pulses, shown here in red. For a hard reset in bottom right, there's no difference in firing threshold for the 3 lambdas chosen. From here, we simulate these dynamics in a neural network to see the implications of this behavior. So since micromagnetics is a little clunky to run a neural network, here I use an analytical model for domain wall motion to use in the network. So under current-driven and field-driven reset, the domain wall remains in the nil position. So the first expression is used here. And due to the slope of the trapezoid, the domain wall moves in Walker breakdown regime. So the second expression is used for that. So a bit about the network and the task. So the data set used for inference testing is the OpDigits data set, which is the MNIST handwritten digits data set, which downsampled to 8x8 resolution. A single layer neural network, or perceptron, is constructed for classification and is comprised of 64 input neurons and 10 domain wall MTJ output neurons, along with 64 by 10 synapses for a fully connected layer. The input neurons and synapses are treated as perfect double precision encoders and weights, and the synapses are pre-trained with 900 images from the OpDigits dataset using stochastic gradient descent. 100 images are separated for the test set, and they're grouped by class. So for example, zeros are all together, then ones are all together, and so on. A varying degree of loculity is introduced by swapping n number of images from each group from 0 to 9. And then inference is run over 3 random seeds to get an average result. And finally, the reset currents are assumed to have a minimum pulse duration of 10 nanoseconds to match realistic devices. So in the first batch of results, in a shape anisotropy-driven reset, inference was done for neurons with varying degrees of delta, which is the physical slope of the trapezoid. The dataset randomness is denoted on the x-axis with classification accuracy and completion time on the y-axis for the top and bottom, respectively. The black dashed line denotes the baseline classification accuracy of 87% at the top figure and completion time of 1.14 microseconds at the bottom figure. So for all 100 examples from the test set. In order for the network to maintain reasonable accuracy for higher dataset randomness, in this case, a rest period of 9 nanoseconds after each classification is implemented. From the results shown for edgier neurons or a softer reset, softer reset in this case is a smaller delta. There's a classification accuracy advantage over the baseline, while there's a significant classification penalty for the higher randomness datasets, shown in the red here. Due to the current density penalty of trapezoidal synapses near the wider edge, there's also a penalty to completion time for neurons with larger delta, which shown in the purple on the bottom here. In using magnetic field-driven reset, with external fields of 10, 12, 14, and 16 Gauss applied, the story is similar. So there's an inference accuracy advantage for the more ordered data set at 0% here. While for a more random data set, we see a performance degradation. However, since magnetic field has a stronger effect on domain wall motion, this effect can be tuned to achieve roughly the same performance as baseline for even a completely randomized data set. Due to the stronger reset effect of magnetic field, a rest period of 2 nanoseconds is applied after each classification. And so that results in an order of magnitude faster classification time than baseline, although the trend of faster classification for ordered data sets is also the same as the previous example. So using reset currents of 5, 7.5, 10, and 12.5 microamps to reset the device, this was chosen intentionally to not completely reset the device after each cycle. And so the results here are similar to the 2 examples before. And the distinction here is that there's a slight improvement in classification time due to the lower firing threshold of certain neurons. So there's some time saved in the integration time. And there's an inference accuracy improvement still over the baseline with ordered data sets at 0%. And the reset current can also be tuned so there's very little classification penalty for randomized data sets. So statistically, not even that different. And there's more things to compare than just speed and accuracy for these 3. And so here I'll discuss a few of the differences. So starting from area, the area usage for both the shape and field-driven resets is lower than the current-driven due to the need for more external circuitry for a reset current. This is only if the external field is introduced through interfacial layers and not by applying external field using external circuitry. For current efficiency, shape-driven reset loses out to the other options since domain wall velocity relies on current density and a wider domain wall, which requires a larger amount of current to propagate. So near the wider edge of the track, there would be a lower domain wall speed. And so therefore, to attain the same performance as baseline domain wall MTJ neuron, a larger current is required for integration. And there's no significant curve efficiency cost for the other types described. No significant difference. The fabrication difficulty for the field-driven device is higher due to the need for interface engineering if external field is introduced that way. But it would be similar to that of the current-driven case if it were introduced through an external wiring, for example. The scalability for the shape anisotropy-driven neuron is lower as well due to the tendency of the domain wall to pin on edge defects since it's a relatively weaker effect. And finally, reconfigurability is pretty important because this enables the device to dynamically adapt to data sets, which would be helpful for online learning. And in this case, the shape-driven one has no reconfigurability ability. But for the field, if it's introduced externally, then there's some reconfigurability possible here. So as a quick summary, edgy relaxed behavior can be implemented in domain wall magnetic tunnel junction neurons through intrinsic properties of shape anisotropy, external field, and modulated current, which enables neurons that are optimized for sequentially repeated information. And there are also opportunities to tune this on the fly, enabling network level optimizations using task-adaptable neurons. So the future direction for this work, I imagine, is towards spiking neural networks. These are networks that mimic the behavior of biological brains more closely and in more energy efficient ways. And since information is encoded in spike frequency as well as amplitude, edgy relaxed behavior should have deeper consequences for this case. All right, thanks for listening. Are there any questions?
I'd like to open the floor for questions. Please remember to raise your hand. All right, if not, I'll start with one, I guess. What is required, like your input pulses, like how much current is required for those? Does it always have to be the same?
It doesn't necessarily have to be the same. So I just set it at 80 microamps because it gave me a reasonable speed. And you can also introduce differences by using spin orbit torque driven neurons instead, which could also greatly improve the efficiency of the devices.
Thank you. Are there any other questions? If not, I think in the interest of time, we'll move to the next speaker. So the next speaker has given a pre-recorded talk, so Saima can share that. And so this talk is from Hannah Bradley from Oakland University in the United States.
Hello, my name is Hannah Bradley and I am a PhD student at Oakland University. And today I will be talking about spike pattern association neuron using antiferromagnetic artificial neurons. First, let's talk a little bit about antiferromagnets. As the result of their anti-parallel spin patterning, antiferromagnets, or AFMs, have a natural frequency in the terahertz range. This allows them to be used to create very fast devices. These frequencies can be excited by a spin current, applying torque to the magnetic sublattices of the AFM. The exchange energy between the sublattices changes, which allows for the terahertz frequencies. The spin current acts on both magnetic sublattices and causes them to rotate, but the anisotropy of the AFMs cause this rotation to not be uniform. The rotating spins create a spin pumping signal, the magnitude of which is proportional to the rotational speed. The non-uniform rotation at a terahertz frequency results in a sequence of very intense, very short spin pumping spikes. The orientation of these sublattices can be described by using the angle phi, which is the angle between the Neal vector and the EZ plane. The derived equation for phi resembles the equation for a mechanical pendulum under a driving force, with the spin torque being that driving force. The anisotropy of the AFM gives the equation its potential, while the damping is a result of the material properties of the AFM. The most important part of this equation is the fact that the exchange energy contributes an effective mass, which leads to the AFM oscillator having inertia. The oscillator can now act like an inertial particle under a driving force, with the driving force being the spin torque from the spin current. When the current is at a supercritical level, the AFM will continuously oscillate by itself. But let's consider a case where the driving force is at a subcritical level, and the spin current alone is not enough to send it into an oscillation. With an additional pulse of current, the oscillator can act as a neuron, overcoming the energy barrier and causing a single oscillation. At the bottom of this sinusoidal path, the change in the angle phi is the fastest, which results in an output spike due to spin pumping. Like all systems with inertia, the rate at which this particle goes through an oscillation depends on the strength of the driving force and the additional stimulus. Now it can act like a very fast artificial neuron, always ready to go and to be set off by an external signal. They are very fast, with the width of an output spike beyond the order of 10 picoseconds, and they are unlike conventional artificial neurons because of this inertia. Linking up multiple of these AFM neurons in a chain allows the output of one neuron to act as the input for the next, so an output spike can travel like a wave through the chain. In conventional artificial neurons, there is an immediate reaction as a result of an input. However, the inertia in AFM neurons causes there to be a delay between a single neuron receiving an input and its resulting output. This delay can easily be controlled by increasing the coupling strength between the neurons. Therefore, we can now control the temporal position of an output spike by adjusting this coupling strength. The synapses used to couple these neurons are constant and easy to implement. A simple copper bridge would be able to carry a spike of spin current from one neuron to the next. This is great when creating simple AFM neuron circuits like inhibitors and memory loops. However, variable synapses are needed to create more complex neural networks. So now we can create AFM neurons and we are able to link them together. The next step would be to start building neural networks capable of more complex functions. Constant coupling synapses are easy to implement, as shown by the copper bridge. More complex synapses are not as easy. A new way to combat the need for more complex synapses in neural networks is to make use of reservoir computing. In reservoir computing, there exists a reservoir made up of multiple neurons all interconnected with each other. However, all these connections are constant. This reservoir is able to receive input and do all calculations needed. The only thing left to do is filter out the relevant information. This is the job of the output layer, and the only layer in need of more complex variable synapses. There are many ways to encode information in reservoir computing. Many learning algorithms use rate-based encoding, where the frequency of spikes within a time window is used to encode information. However, this would not be possible with AFM neurons. There is a refraction time within AFM neurons, where if a neuron receives a second input too close to the initial input, there will not be a second output spike. This refraction time would cause unintentional inhibition of important spikes within the time window. Instead, reservoir computing with AFM neurons will use temporal encoding, where the information lies within the timing of the input spikes. In this presentation, we make use of a system called Spike Pattern Association Neuron, or SPAN. SPAN is an example of reservoir computing because only the weights of the output neuron are adjusted. The span has a number of inputs, and they all enter the output span through variable weights, which can be trained so that the span will output a spike train matching the desired spike times. Here you can see what would be the start of the learning process. All the variable weights are the same, and clearly the output does not match the desired output. After several iterations of training, each weight to the span has been changed so that the resultant spike train matches its target. The span uses a learning rule based off the Widrow-Hoff or delta rule. This rule uses the difference between the desired spike time and the actual spike time of a neuron to update its weights. The lambda is a real value, positive, and constant learning rate. The higher the learning rate, the more aggressive the change in the weights are. The final equation for an AFM span algorithm is shown here, and we can see this learning rule in the graph shown. The takeaway from this equation is that when the actual time is greater than the target time, the weight will increase. When the actual time is equal to the target time, it will stay the same. And if the actual time is less than the target time, the weight will decrease. Here we show a successful simulation of an AFM span with 3 inputs. It is clear to see from the bottom panel that in under 20 iterations or epochs, the span is able to successfully map its output spikes to the desired times. The top panel shows the percent error between the span output spike times and the desired spike times. It rapidly decreases and ends around 0.02% error. It is possible to connect two AFM spans to the same inputs. Each span is trained independently to different target spike trains. You can see this clearly in the graph on the right. Each span reaches its target spike times within 20 epochs and is unaffected from the spikes of the other span. Multiple AFM spans with the same inputs are great when the inputs are simple. However, spans are limited by their simplicity and would not be possible to use for more complex inputs. In order to keep the need for complex variable weights to a minimum, reservoir computing is still the best option when building neural networks with AFM neurons. We propose, instead of a simple one neuron output layer like span, a more complex output layer capable of higher functions. We have previously investigated inhibition circuits and have found that they are easy to implement with AFM neurons because of their effective inertia. These types of circuits would be an integral part of the more complex output layer because they only used fixed weights. This output layer would be able to further filter more complex inputs while still keeping the need for variable weights to a minimum. We are currently working on this concept for the use of encoding more complex inputs like Morse code, where the alphabet is made up of multiple dots and dashes to be encoded into spike trains. In summary, antiferromagnetic materials resonate at a terahertz frequency range and can be used to create ultra-fast neurons with an effective inertia. We can take advantage of reservoir computing to create a neural network with AFM neurons where only the output weights are trained. A spike pattern association neuron, or SPAN, makes use of reservoir computing and the delta rule to train incoming spike trains to the desired output spike trains. Thank you all for listening, and thank you to the organizers for their accommodations and flexibility during these times. Please feel free to contact me with any and all questions at hbradley@oakland.edu. Thank you.